Okay, good morning everyone. Welcome to APNIC eLearning web class. We'll be discussing about OSPF Basic. Okay, so in OSPF Basic, what we'll be covering is all basic concept of OSPF, so that it will help us to understand OSPF better before we start configuring it. Okay. Little bit about introduction before I start the actual presentation. My name is Nurul Islam Roman. I am currently the senior training specialist now at APNIC. I am in APNIC since in 2006, and as you can see on the slide, I have got interest on some areas that has been already listed on the slide. So if you have any question in context, feel free to ask the question anytime. And to ask the question, you don't need to wait till the end of the presentation. So just write or type your question on the chat box. I will try to keep my eye on the chat box when I'll be presenting. So yeah, and I'll try to answer your question as quickly as I can. This is what an overview about OSPF today. We'll be discussing about the basic features of OSPF, what is link state routing protocol, and some convergence features. And obviously OSPF is one of the protocol that ensure faster convergence. Then we'll see how OSPF basically operate, right, from the point when you configure it, and then afterward it start building the adjacency, and how it try to create and maintain the routing table. Then we will see the neighbor discovery process, which is going into further detail throughout the process, what are the steps that involves, and then we'll discuss about OSPF packet types and formats. So just to give you some ideas about OSPF packets, so that it will help you to do troubleshooting when you need to do it on OSPF adjacency, and when you run the OSPF. Then we'll try to introduce some topology that OSPF supports, and how OSPF build adjacency on different topology. Okay. So OSPF is basically shortest path first protocol. So shortest path first is a protocol that is standardized in IETF. So since IETF has been standardized this protocol, so this protocol can work on the multi-vendor platform. So for example, if you can have a Cisco router with a Juniper router, you still can run OSPF because it's an open standard protocol. It is designed for TCP/IP environment. So when OSPF they exchange their messaging, and they build the topology table, and they build the routing table, all the control message they use runs on IP. So since OSPF use IP as a control protocol, so OSPF will only run on IP environment. And the protocol number for IP to run OSPF is 89. Currently, we have got two versions of OSPF, version 2 and version 3. Version 2 supports IPv4, and version 3 support IPv6. Okay, so if you need both version 2, if you need both IPv4 and IPv6 running on a router, you need to run both OSPF version 2 and version 3 at the same time. It doesn't mean if you have version 3 that support version 2 automatically. No, for two different protocols, you need two different processes to run. Version 2 process and version 3 process. Okay. So as a link state routing protocol, how OSPF works, if you see all those routers, the way they are connected, so after the connectivity done, and then you configure OSPF, all those routers on the diagram, routers Z, Y, X, and Q, they exchange some information, right? So what information they exchange? They exchange the link state among all those connected routers connected network. So for example, router Q if they have got four interface connected and those interfaces are participating in OSPF, they carry link related information. For example, what is path cost, delay, and MTU, and all sort of other factors. Based on that, when those information are sent to all the routers on the same area, then they try to put that particular router on top of the OSPF tree and calculate the best path. So in the link state routing protocol, since they exchange the state of the link among all the routers, right? So each and every routers, when they select the path or the best path, those best path from the reference point of view of that particular router. Okay, it's not like distance vector protocol. In distance vector protocol, if I need to compare it, the routers, they don't send the link state, but they send the whole routing table to the connected routers. So this is how routing by humors can happen. Okay, but OSPF is much sophisticated, or link state routing protocol is much more sophisticated than distance vector counterpart. So what is the link state routing? So in link state routing, as I said, they do not send the whole routing table periodically, right, to maintain the routing information, but they manage three separate tables. Number one is our neighbor table, then topology table, and then routing table. So maintaining all those three tables, they keep different information in those tables, right? So based on those information, they try to find the best path by using shortest path first algorithm, right? We have a slide to explain detail how shortest path first algorithm can be used to select the best path, and how link state routing protocol, they maintain the routing information, since they are not sending the routing table periodically. They send small hello in certain interval, right? Hello is very tiny packet. So this is how OSPF makes sure they optimize the link bandwidth. So by sending a tiny hello message, OSPF, they maintain the link information. If the link goes down and if the hello message doesn't come for the next interval, then OSPF trigger itself, there is some problem on that particular link because I'm missing the hello. Okay, and this is how it sends a trigger update to other routers, let them know I have identified a link failure in the network. Okay, so this is how link state routing protocol works. In the link state database, what are the databases that I have explained in the previous slide? All the link state routing protocol, they maintain neighbor table, topology table, and routing table. What they maintain neighbor table? Okay, neighbor table is the first table they build since after you configure link state routing protocol. For example, OSPF, in the neighbor table, they try to first build adjacency or neighbor relationship with the neighbors, right? So they exchange some message, hello message. I'll explain what are the parameters that need to match on the hello, and based on that, they build the neighbor table. When the neighbor table has been built, they put all those neighbors into the neighbor table. We call it neighbor list, or list of the neighbors. Then among all those neighbors on the neighbor table, they exchange topology database. As I said, topology database means in every routers who are participating in the link state routing protocol, they maintain the link related information. For example, the prefix connected, cost of the link, network address, and all sort of other information. Okay, then from the topology table, if any particular router learn more than one path to the same destination, then the question comes to select the best path, right? Even like, if they receive only one path, then still they need to select the best path. So SPF algorithm used to select the best path from the topology table, right? So when the best path has been selected from the topology table, obviously they consider a factor to select the best path. That's what we call metric. By calculating the metric, they select the best path if there are more than one path to the same destination, right? And then the best path goes to the routing table. If there's only one path in the topology table for the same destination, well, that will be the best path, and that is the only candidate for the best path anyway. Okay, this is what the slide that will tell you in more detail how SPF or the linked state routing protocols select the best path. So for example, if you see the routers here are connected the way they are all connected, right? All those routers are A, B, C, D, E, F, G, H, and X on top, right? So when they are connected, so for example, if you see all the routers after the connectivity, OSPF is configured, all the path costs are 10, right? So if they exchange all the topology information, and after that, if router X need to select the best path, so for example, to go to destination F, how OSPF or the linked state routing protocol will be used, and how SPF algorithm will find the best path. So for example, from X to go to F, what it knows, it needs to go via, one path is via A, D, and then F. So if you calculate the path cost, 10 plus 10, 20, and 10, 30. So if X need to go to F via path A, D, and F, then path cost is 30. Well, the alternate path that it has got X to D and D to F, then 10 plus 10, 20. And the other path it has got X to C, C to D, D to F, then 10 plus 10 plus 10, 30. So this is how he calculates all available path from that particular router to the destination. And by adding the path cost, they'll create a shortest path first tree, right? And if you see the tree, this is how they build the tree. So this is what one path, this is what other path, right? This is how they build the tree, and on the tree they calculate the path cost. So by calculating the path cost, now it's easy for the algorithm to select the best path, because it knows the path cost of all the available path it has got. Okay. So link utilization, OSPF they consume the low bandwidth from the link, right? For example, how it consumes the low bandwidth, they only propagate changes, right? And they use multicast. As an example on the slide, if you see on R1, if R1 detect the link failure here, right, then what R1 will do, R1 will send an update message to the neighboring routers along the path, and the update message is sent on multicast. So it is sent on multicast. Then router 1 don't need to create so many messages. It's like unicast messages. If it has got 5 or 6 neighbors, if it's unicast, then router 1 might have to create 5 or 6 individual packet as an update. Since OSPF use multicast, router 1 only use one packet, and packet destination is the multicast group address. Since the multicast group address is the packet destination, right, it will copy that things to all the connected networks. And this is how it propagates link related information. And since it uses periodic updates and sort of multicast, this is how OSPF will ensure low bandwidth utilization. Okay. Faster convergence, how OSPF will ensure faster convergence. Convergence is a factor based on that we really select appropriate routing protocol. Faster convergence means the protocol or routing protocol can be able to forward packet, right, from the point you configure the protocol, routing protocol, to the point the router is ready to forward the packet. That's what we call convergence time. Or if any network change happen, then the routers knows there is a change in the topology. So from the point it identified the topology change to the point it starts forwarding packet again is a convergence time, right? So normally when we select a routing protocol, we try to make sure the routing protocol who can ensure Faster convergence quickly can identify the network change and then start forwarding the packet. It's a better routing protocol. OSPF ensure that faster convergence. How you do that, or how it perform in that way? So for example, R1 connects to R3, right? So this is what the primary link, and then via R2 is the secondary link. So from R1 to R3, if the path has been changed, right, the primary path, this network is down, the primary path has been changed, then what R1 will do? R1 send a trigger update, right, to R2, and it goes to R3. So when R3 knows, when the update goes to all the other router, so then all the routers, they will select the alternate path, which is the path via R2 from the topology table, and it goes to the routing table of those routers. So this is how they ensure the faster convergence. Since the alternate routes is already in the table, it just needs a trigger update, and then quickly it will select the alternate route or second best path, and it will be installed into the routing table. Okay, so that's how it's going to ensure faster convergence. Okay, when OSPF they send or they identify the link failure, it send the update based on the flood, and obviously it works on multicast, and then when that update has been propagated across the other routers, all the other routers, they send an acknowledgement. So for all update there is an acknowledgement. That obviously ensure the reliability of the routing protocol. Okay, and then quickly all the router will be updated, they will send an acknowledgement, then across the areas all the other router, they quickly knows the path failure, and they can install the best path. So let's have a look the basic OSPF operation. As I said, OSPF, when you configure it, first thing what it will do, it will find its neighbor. We call it neighbor discovery process. Then it will exchange the topology table, right? And then when the topology table has been synchronized among all the routers, then they use the SPF algorithm to select the best path. When the best path has been selected, then it will be installed into the routing table. So let's see the first step of the process. When you configure routers, so for example in this slide, 3 routers are connected to a switch, and you configure OSPF on all those 3 routers, right? So then on the connected interfaces, they find a link, OSPF link, and it starts sending a hello message. So since it's a multicast hello message, a single message will be propagated to all the other routers. Same way, all the other routers will send the hello message, and then other routers on the other side of the network, they'll receive the hello message. So when OSPF routers, they are just configured, we call it at a downstage, and from the downstage or state, they send a hello message to the neighboring link, right? The links are configured with OSPF. They send that hello message on multicast, as I said. For IPv4, multicast group address is 224.0.0.5. For IPv6, multicast group address is ff02::5. So when the multicast message has been sent, this stage, when each routers they send the multicast message, we call it init stage or initialization stage. At the initialization stage, they sent the multicast hello message. Then on the other side, the routers, when they received it, they check some attributes on the hello message, and if it match, right, they also send their own hello message, and if on both the routers those parameters match, then they build the adjacency. But when they exchange the hello message, both of them, we call it two-way stage. In two-way stage, they both exchange the hello message, right? So in the hello message, those parameters normally they send on the hello, and those asterisks, red asterisks, are actually the attributes need to match, must need to match before they build the adjacency. Okay, after the two-way stage, this exchange the summary database, right, which is the topology database. And when they exchange the summary database, now the question comes, who will start first, right? Then they need to decide who will start exchanging it first. The router who has got the highest router ID normally send the topology database first. We call it a start stage, when they decided who will send it first. And then when they exchange the topology information, we call it exchange state. After the exchange state, what they did, they sort of verify those into their existing topology table. And if they realize some of the network information are new, they haven't learned those before, right? Then they ask for a detailed one, right? And then the neighboring router need to send the detailed topology information. And when the detailed topology information has been exchanged, we call it full or loading stage. Okay. Okay. So when they exchange the topology information, then they will use SPF algorithm to build the routing table. After they build the routing table, now the question comes, okay, how they will maintain, because after they build the routing table, when they are in the convergence state, they start exchanging the packet. But how they maintain it, how they maintain, like, you know, in times if they receive any updates about the same network from other neighbor, right, it could happen. Then how they know the update that it has received and the update it has got, which one is the latest one, right, which one is the authentic one? They maintain all those link related information, as I said, by sending a hello message. Hello is a very tiny, and that's sent on every 10 seconds, right? Every 10 seconds, very tiny hello packet are exchanged on all OSPF link of the router. If there is any topology change has been detected by any routers, right, either by link signaling of that particular router or by an update from a neighboring routers, they send a trigger update message to the other neighbor in the neighbor table, right? When the trigger update sent, this is how they knows the link information has been changed or not. Then when the update goes, what they will do, they will check the update came and the update already, or the entry that already in the topology table, and there will be a sequence number on every update, right? Sequence number is a 32-bit number. So when the sequence number comes, they check the update came and the entry that the router already have, which sequence number is the latest one. If the one just received is the latest and the one already in the topology table are the old by the numbers, right, then they will replace it. If not, if the one they receive is the older number and the one already in the topology table is the new number, then they copy that existing one back to the source. This is how they maintain the routing information. OSPF packet type. As I said, when OSPF they exchange the routing information, there are 5 packet type they use that start from hello, which is type 1, that exchange in every 10 seconds in the LAN network or LAN type of link. Then DBD, database descriptor packet, which is type 2, that contain the database related information, right? And LSR, link state request packet, which is type 3. Type 3 packet is when OSPF receives the summary database, and if the database is not in the topology table or the entry is not in the topology table, right, they ask for a detail of that entry, and for that they send a message which is called LSR or link state request packet. Then link state update, LSU packet. What is that? the detailed information when that receiving router send back to the sending routers, the detailed update message goes to the sending routers via a packet called LSEU, or link state update package or packet. The last one is acknowledgement, which is type 5. For all the update message, every routers, they need to send an acknowledgement back to the source. Since they use IP is connectionless, so that's why OSPF use their own acknowledgement. Okay. So format of the OSPF packet, if you see the format of a OSPF packet, so the OSPF packet itself is encapsulated within your layer 2 frame, right? And then you have your regular normal IP headers, and then as a payload the OSPF packet will go. So if you see OSPF packet itself, it has got the version numbers, type of the packet, packet length, router ID, area ID. Router ID is the sending router's router ID. Checksum to sort of check the link errors, authentication type if there is an authentication type, and then data. So those are the protocol field that we have within OSPF packet. Okay, so if it is an acknowledgement packet, right, definitely the payload part or data part will be empty in OSPF. So those are the information that OSPF normally carry in OSPF packet. As I said, the version number, packet type from 1 up to 5, the length of the packet, because it has got data is variable here, that's why they need to define how big the OSPF packet is. Then area ID, which area it belongs to, router ID, the sending router or source routers router ID. Router ID normally 32-bit number that we can configure on the OSPF router, but in the service provider network normally the loopback address is used, so loopback address by default will be the router ID. And if you use any OSPF authentication, then that will be included into the authentication type. So content of the OSPF packet, what could be the content for the hello packet? On the hello packet, the data part contain the list of the neighbors that it has got, right? For the DBD packet, data part contain the summary of the LSDB, which includes all the router ID and sequence numbers and all the other information, for example, prefix, length, subnets, and all the things. For link state request, what could be the part of the data, or what could be the payload part of the OSPF packet that contain the type of link state update needed, right? What link state update I need, that's why I send the link state request packet, and obviously the router ID. Link state update, what it contain on the payload part, obviously that contain the topology detail information. And as I said, on acknowledgement, the data part or the payload part is empty. There is nothing on the payload. So if you see the difference between OSPF version 2 and version 3, normally in OSPF version 2 and version 3, OSPF packet type hasn't been changed that much, right? Only IP packet has been changed, so that on the main IP header will be changed, right? And OSPF packet type will be as it is, except the authentication, because OSPF version 3 authentication is not included into the OSPF packet that use the regular IPsec available for the IPv6 protocol. Alright, so to send this packet in IPv4, they use a group address which is 224.0.0.5. In IPv6, the group address is ff02::5, right? Okay, OSPF network topology. Normally when OSPF they build adjacency, right? When OSPF build adjacency, the adjacency building behavior depending on the topology has been used. In different topology, the adjacency building behavior is different. So for example, if the routers are connected in a LAN type of topology, right, on a switch, then probably they need to select the DR and BDR. I'll explain what is that. It's not a point-to-point link. We call it broadcast and multi-access network, right? And if OSPF routers are connected into a point-to-point link, right? So the neighbor relationship behavior is different in point-to-point link. And if OSPF routers are connected into an X.25 networks, so that's what we call non-broadcast multi-access. The OSPF neighbor relationship behavior will be different. Probably need to configure our neighbor manually on that topology. Let's have a look. So in broadcast multi-access networks, so this is sort of a LAN type of network. In this LAN type of network, since all the routers connected, they will be exchanging lots of OSPF packet, and those are sent in a multicast group address. That's why if we have more than like 10, 20, 50 routers on a same LAN network, there will be a significant amount of OSPF related control packet will be carrying right across the network. And to ensure a discipline of exchanging the message among all the OSPF enabled routers on a LAN network, they select a DR designated routers and they select a BDR backup designated router, so that all the updates will be sent by other routers to the DR only and BDRs, and the responsibility of the DR is to reflect this information back to other routers who are DR others, right? So this is how in broadcast multi-access network they exchange OSPF control information. As I said, in a broadcast multi-access, for example LAN network, we need to select, or the OSPF protocol will be selecting a DR and a BDR, right? If you don't do anything, just by identifying the protocol, by identifying the topology, OSPF protocol will elect a DR and BDR. There is a default behavior how they elect DR and BDRs. Normally the highest router ID will be the DR, and second highest will be the BDR, and other routers will be DR others. Into a point-to-point network, since only two routers are connected, so there is no requirement to build DR and BDRs, right? So they all will be neighboring routers. So we call it full neighbor relationship. But in DR BDR environment, DR others and DR and BDR will have a full neighbor relations, but with other routers, like regular routers within that broadcast multi-access network, they will build only up to two-way relationship. They only exchange the hello, that's it. Okay, and in non-broadcast multi-access network, we need to configure DR and BDR manually, right? When we add neighbors by adding a neighbor statement, then they will exchange their hello message and all, and they'll select their DR and BDR. Okay, but we have to configure neighbor manually. So in broadcast multi-access network, normally OSPF use Ethernet or tokening type of topology. As I said, neighbor relationship are created automatically. They elect DR and BDR, and they exchange OSPF hello in every 10 seconds. So when they exchange neighbor relationship every 10 seconds, then the dead interval is 4 times. What is dead interval? Dead interval is when OSPF identify any neighbor is down, right? So they don't just remove that neighbor straight away from the neighbor table. When they don't receive the next hello, in one hello is missed, then they wait for another 3 hello to be missed before they declare them as dead. So altogether 4 hello need to be matched, or need to be missed. 4 hello packet need to be missed before they declare any neighbor as dead. Broadcast multi-access network, as I said, when they elect DR and BDR, normally the multicast message from DR others going to DR and BDR will be sent on a different multicast group address, which is 224.0.0.6. So when any normal router send any multicast message to 224.0.0.6, only two routers will be receiving it, which are DR and BDR, right? And then DR and BDR, when they reflect message back to the other routers, right, they send using regular multicast group address, which is 224.0.0.5. In IPv6, 224 FM02:5. Alright, then they build up the adjacency, and as I said, they will build full adjacency with only DR and BDRs, right? But among other routers, regular routers, they will build two-way neighbor relationship. DR BDR election process, how DR BDR election will be performed. As I said, router with the highest priority value normally will be DR, right? And second highest will be BDR. But in our network, we normally see all the router has got the same priority. So if it's Cisco or other routers, if the router has got the equal priority, then what they'll do, they'll use the highest router ID as the DR and second highest as the BDR. And based on the router ID, they'll elect DR and BDR, right? So if we don't configure the router ID on a router, so they'll take the first loopback address as the router ID, okay? And DR BDR election is non-preemptive. What does it mean? It means when DR BDR election is done, if new routers is joining in on the network, right? And if the new routers who is joining on the network, he has got the highest router ID, not necessarily they will recalculate the DR BDR election, right? So already DR BDR selected. So the new router, when they'll join in, even though the router ID is highest, but they will not be the DR and BDR. As I said, in point-to-point link, where we normally use PPP and HDLC type of protocol, there is no requirement of DR and BDR, only two routers, that's why. So neighbor relationship will be discovered automatically, and hello message will be 10 seconds as it is, and data interval is 4 times of the hello, which is 40 seconds. In non-broadcast multi-access network, in this type of network, as I said, there is on the layer 2, message are not sent as a broadcast like in Ethernet. So we need to rely on the virtual circuit. Based on the virtual circuit, the link will exchange, the layer 2 will exchange the signal, right? So that's why on non-broadcast multi-access environment, we need to configure neighbor manually, right? When you configure neighbor manually, then based on the router ID and priority, they'll elect the DR and BDR, right? In non-broadcast multi-access environment, OSPF send hello in every 30 seconds. Data interval is 4 times, which is 120 seconds. Okay, so that's the end of the presentation for today. I hope the presentation will be useful, and I'll give you an URL. That URL is here. You can use to give us a feedback, and your feedback is very important for us to improve our future learning session. Okay, so the URL is survey surveymonkey.com/APNIC- That's the URL you can use to give us the feedback. So when you finish the feedback, then it will redirect you to an FTP site. From there you can download the presentation materials that we used today. Alright, so I think that's the end of the presentation. Is there any question by any chance? Okay, so if you have a question, you can ask the question now. Otherwise, if you have the question later on, you can send your question to our email address training@apnic.net. We'll try to answer your question. Otherwise, alternatively, you can come to APNIC help desk. The way you can come to APNIC help desk is in here. We have our phone, email, or even you can come on a live chat. So yeah, so that's the end of the presentation for today, and thank you very much for watching the presentation.